All right. All right. Real quick, get the code. All right, you just made it. Okay. All right. So hopefully you enjoyed the 3-day weekend. Let's get started. So we are recording. For those of you who watched the recording back, I don't know why, but for some reason the camera that's showing up really bright. So I'm not sure why, but we'll deal with that another day. Okay. So in terms of announcements, so I've got all the attendance grades up to date. Homework 2.1's been graded. My TAs are still working on homework 2.2. No real big major hiccups. I think everybody generally understands the concepts there. I do have the solutions for homework 2.1 and 2.2 posted now. They're openly available. Homework 2.3 is due today. Then homework 2.4 will be assigned today, due on Friday. So I think we're gonna, for the next few lectures, the operational pattern is going to be pretty self-explanatory. You know, we'll have a lecture, have an assignment, do the following lecture, and we'll keep on trucking. Now, what's going to happen for the exam is you're not going to have a homework assignment due on the day of the exam or due on the day of the exam review. The idea is that we'll come in for the exam review and ask questions. That's not going to happen like in the next lecture or so, but we are going to have our first exam in the not too distant future. So I just want to make sure that everybody keeps that in the back of your head. Okay, not next week, but the week after. Okay, sound good? All right, so with that, let's get into the wonderful world of static equilibrium. I downloaded our slides today, so hopefully the formatting and whatnot's a little kinder. So, okay, I don't want to edit. I just want to get into it. Let me check something real quick. So, yeah, okay. Format seems to work pretty well. Okay, so this is going to be kind of an odd thing to say, but we're finally going to start doing some statics today. So we've been, for the past few lectures, I would argue that what we've been doing for the past couple weeks has been sort of exploring our vocabulary for this class. So understanding what forces are, understanding what vectors are, how to add vectors and so on and so forth. But we really haven't done anything with them, or we haven't explored these in sort of an engineering context. And so that's what we're going to start doing today. And so what we're going to start doing is looking at static equilibrium of particles in 2 dimensions. Later on, we'll extend this to 3 dimensions. But in order to deal with problems, with static equilibrium problems, there's a particular class of math problems that we have to review, which is how to solve systems of equations. So because we're dealing in 2 dimensions, we're going to start off by dealing with 2x2 systems. Later on, that'll extend to 3x3. Everybody in here has done this at some point or another. It's just probably been a while. So I kind of want to review it. And I want to make sure that everybody understands this is an engineering course. This is not a math course, okay? So in terms of how you solve these equations, I'll be honest, I don't really care how you solve it as long as you get the right answer. And there's oodles of different ways to solve these types of problems. And I'm going to review 3 methods. I'm actually fine with any method that you use, but I think since we are engineers and considering the types of problems that we're going to be dealing with, the easiest thing to do is to just use your calculator, because a lot of the scientific and graphing calculators that you all have as engineering students have baked into them functions that will solve problems like this very easily. And so let's go ahead and get to it. So what we're talking about is a classical problem from algebra that looks something like this. Okay, so the problem is you're given 2 equations that have 2 unknowns associated with them. And this would be true for n equations with n unknowns. It could be 3x3 or 4x4, be what have you. But I'm going to just keep it simple, and we're going to restrict this to 2x2. So I'm given 2 equations. Let's say I'm given x plus 2y equals 3, and I'm given 2x plus 3y equals 4. And I have to find the magic values of x and y that satisfy both equations. Okay? Now I'll go ahead and tell you the answer to this problem. The answer to this problem is that x is -1 and y is 2. Okay? And let's test that. So -1 plus 2 times 2 is 4, so -1 plus 4 is 3. And then on the bottom one, -2, so that's -2 because 2 times -1 is -2, plus 6 is 4. Okay? And I propose to you that that pair of numbers, x is -1 and y is 2, is the only pair of numbers that satisfies both equations. Okay? Graphically, what we're looking at is if I were to graph each of these functions, they would be lines, right? I could take these equations and rewrite them in y equals mx plus b fashion. So I get a line here and a line here, and so that point that I'm talking about, that x is minus 1 and y is 2, that's the point where those lines intersect. So there's only one place that those two functions are equal. So the goal of this problem, this classical sort of set of problems in algebra, is being given a system of simultaneous equations and to find the values of the unknowns that satisfies all of them. If you ever take a course in linear algebra, this is literally the only thing you do in linear algebra. The entire class is devoted to solving problems like this because they show up all over the place in all areas of engineering and science and computations, programming, you name it. I mean, linear algebra is how the world works. It's how your iPhone works. I could go on and on about it. But in here, we're starting out with very basic problems. There are really three, I would say, very practical approaches to solving a problem like this. The two ones that you're probably most familiar with from either high school or maybe Math 127 or Math 132 or something like that are the procedures of substitution and elimination. The other is to use matrix algebra, in other words, like what your calculator will use, and I'll show you how to go through that. So let's go through substitution to make sure that everybody kind of remembers what we're talking about here. So here's what substitution is. So first thing we do is the way that substitution works is we take one of these expressions and we isolate one of the variables. So let's take this first expression, x plus 2y equals 3, and let's isolate x. So let's take the 2y, move it over here, so I get x equals some pile of junk. In this case, 3 minus 2y. Okay? Then what I will do is take this baked expression, this x equals 3 minus 2y, and I will take that and I will substitute it into the other expression. So the other expression is 2x plus 3y equals 4, and instead of x, I will replace that with this, 3 minus 2y. Then I go through and I do all of my algebra, I distribute the multiplication, I combine the like terms, I solve for y, and I get y equals 2. Then I can take y equals 2, plug it into whichever expression I want, it doesn't really matter, and I will get the other answer, x is minus 1, and there's the answer. Okay, so that is the method of substitution. Okay, that is a procedure that we can use to solve simultaneous equations. It is arguably the simplest procedure, at least initially to understand. I will go ahead and tell you that most computational engines don't do substitution, they do elimination. So if you ever use how many of you have experience with MATLAB, I imagine by this point? So MATLAB doesn't do substitution, MATLAB does elimination more often than not when it solves systems of equations, but we're going to show you that here in a second. Everybody okay with this? This is something, has everybody seen this before? Okay, all right, you should have seen this at some point. Okay, so now let's look at elimination. So elimination, what the deal with elimination is we take one of the expressions, so let's take the first equation, and we multiply the entire equation by some magic value. And what I'm doing here is I'm multiplying it by -2. The reason why I'm multiplying it by -2 is I want to match one of the coefficients in the other equation. So if I multiply this entire first expression by -2, I get -2x minus 4y equals -6. The reason why I picked -2 is because see how I have a -2x? Well, in the other expression, I have a positive 2x. That's what I mean by matching the coefficients. So what I can do is literally take those equations item by item and add them together. And by doing that, what I'm doing is I'm saying, okay, what is 6 or -6 plus 4? It's -2. What is -4y plus 3y? It's -y. But then -2x plus positive 2x, I have in fact eliminated x. X is no longer a factor in this expression, hence the term or the method of elimination. So I take this and I get y equals 2. I plug in y equals 2 into either one of the other expressions and I get x is minus 1. There you go. Most computational engines like MATLAB, when you give it a system of equations, it's doing elimination. You might ever, if you ever are in MATLAB land, if you ever hear the term Gaussian elimination, that's basically what it's doing. It's taking these coefficients, organizing them in a big table that we call a matrix, and then it's just performing these operations until we get to our final answer. So, make sense? Now these are very classical problems in math, science, engineering, the solution of 2x2 systems, the solution of 3x3 systems. So classical that just about every single person in here should have a calculator that has these functions baked into it. For example, so what do these functions mean? So let's talk about the math behind this. So the third method is to use matrix algebra. So if you ever hear me use the term matrix algebra or linear algebra, it's the same thing. You say linear algebra because these represent lines. That's where that term comes from. So we take this set of equations and we write it in matrix form. And so what that means is, so if we look at this system of equations, so the 3 and the 4, that becomes a column of values. The x and y becomes a column of unknowns. And then 1, 2, 2, 3, this is my matrix. And where do I get this? Positive 1, positive 2, positive 2, positive 3. Okay? So I could take this expression and rewrite it in matrix form. And I have a feeling you all have probably done matrix multiplication at some point. You all have seen that before, like when you multiply a matrix times something, you're doing this times this, that times that, this times this, that times that, right? So this is just taking that expression and rewriting it. The idea then is if I have my term written in this fashion, the idea is that you can solve for x and y by taking this expression and multiplying both sides by the inverse. So I have this expression here. If I multiply both sides by the inverse of this matrix on the left, if I have this times its inverse, it cancels. So over here on the right, I get the inverse of this matrix times this equals negative 1 and 2. Going back to linear algebra, probably the fundamental challenge in linear algebra is determining how to find the inverse of a matrix. That's literally what the whole class is about. Now, 2 by 2 systems, there's actually a very nice plug-and-chug formula for determining the inverse. 3 by 3 systems, it can get a little computationally intensive when done by hand. And if you start getting into 4 by 4 matrices, 5 by 5 matrices, or anything bigger, doing that by hand becomes just an absolute pain. The whole point is, can we develop a systematic means of doing that maybe with a computer or a calculator? Of course, you can. Now, let me show you how this is done in a Casio, but other calculators are going to have a similar option. So the way that you would solve this in the Casio is if you have your Casio with you, for those of you that have one, okay, if you go into mode, all right, so the mode menu should bring up something like this. There are 8 options in the mode menu. When you are normally operating the calculator, you're in mode 1. That's computational mode. You're going to go into mode 5. Mode 5 is your equation solver, and there's oodles of options there. So we can solve, so like option 3 would be solving quadratic equations. So you put in A, put in B, put in C, and it does the quadratic formula for you, gives you an answer. So this is the cubic equation, but what we're interested in right now is option 1 and option 2. Option 2 is for 3 by 3 systems. Option 1 is for 2 by 2 systems. So what you do is you go to mode, 5, and then 1, and then you'll see a table that looks something about like this. And all you do is you enter in your coefficients. So you do 1, 2, and 3, and that comes from that first equation. 1, 2, 3, and then 2, 3, 4. 2, 3, and 4, and you just hit enter to each value, and then when it's all said and done, you hit enter again. It will tell you, boom, that's x is negative 1, that's y is 2. This is how it's done in the Casio. Other calculators will do this for you as well. What I will probably do is after lecture today, is I did this last year. It's to the Teams channel. I posted a little playlist that said, here's how to do it on a TI-89. Here's how to do it on a TI-83. Here's how to do it on a TI-36X. Here's how to do it on this calculator, so that everybody kind of is exposed to this. I do tend to think that the Casio is kind of a good calculator to have as an engineering student because it's approved for the FE, and I think dollar for dollar, you get the most bang for your buck with the Casio. But I don't really care what calculator you use. So, everybody okay with this? Okay. So we'll get into the specifics of this a little later and how it fits into static equilibrium. So let's talk about static equilibrium. So what we're going to be dealing with initially are sort of problems like this. So this is an overhead crane lifting an element in some sort of foundry or mill type scenario. And so the idea is, okay, I have this weight that is applying a downward force. So what is the required tension in these cables to keep the element in equilibrium? Whether I'm talking about some element in a foundry or some kid on a zip line, it's kind of the same idea. So what we're going to be dealing with is problems where we're considering situations in static equilibrium. What does static equilibrium mean? Okay, so up until now, what we've done is this. Okay, so what that means is we've been given a system of forces that are all applied at a common point, and we understand how to add those forces together, right? So we could do that graphically, we could do that trigonometrically, or what I think we have found is the most systematic means of doing that is to take these vectors, express them in ij notation or ijk notation later, and add up the I components, add up the j components to get a resultant, right? Make sense? So what we're doing is taking a system of vectors and then resolving that into a single vector, a single resultant vector. That is some component in the x direction times I plus some component in the y direction times j. Now, what that is doing is just taking a system of vectors and resolving it into one. We are not getting into statics land with this. Okay? Now what we're ready to do is introduce the concept of static equilibrium. Now, what I want to do is I want to just recall Newton's first law just to understand what we're talking about here. So an object that is at rest or in motion will remain at rest or at motion until acted upon by an outside force. So what that means, all in a nutshell, is this. Okay, so let's take me standing upon this stage right here. So I have a weight, right? And if we were to express me as a vector, my weight as a vector, it would be Greg equals some weight this direction, right? Some magnitude, some direction. And it is acting this way, right? Now, if this floor were not here, what would happen? I would fall, right? Right? I mean, any object that is, not acted upon by an outside force, if I let it go, it falls, right? But notice right now, it's not moving. Just like me, I'm not moving vertically, right? Because what's going on right now is I am applying a force downward to the floor. The floor is responding. It is reacting with an opposite force acting upwards, right? So if we were to look at this mathematically, me right now, considering vertical action, the sum of those forces is 0, right? Okay? So there is a magnitude of force acting downward and an equal and opposite magnitude acting upward. The sum of those forces is 0. For static systems, one of the most fundamental equations we will deal with in the entirety of this class is that when we are dealing with static systems, the sum of forces is 0. Okay? Bar none. It is probably one of the two most important equations we will exploit this entire semester. That for static systems, the sum of forces is 0. We will add to this a second, more important expression, or just as important expression later, which is that for static systems, the sum of moments must be 0. We're not there yet. That's after the first exam. We'll get there. Now, what this means for vector notation is that if I look at this in 2D systems, I have the resultant equals 0, but what is the resultant? It is the sum of all the forces in the x direction times I plus the sum of plus all the sum of the forces in the y direction times j. But that resultant must equal 0 in static equilibrium. So in static equilibrium, I can basically resolve this expression into two equations. The sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. There we get a system of two equations, and we will see these equations in the systems that we deal with in engineering. Two equations, two unknowns. Okay? Now, the best way, I could show you these expressions till we're blue in the face. The best way to understand how to employ them is to do some examples. Now, before we do that, we do have one more item to review, and I want to make sure that everybody is familiar with this. This is going to happen on this in this class on homeworks. We are dealing in forces. We are dealing in the sum of forces equals 0. We are not dealing in the sum of masses. Okay? Very commonly, you will be given a problem and you will be given a mass. You must convert that to a weight using the acceleration due to gravity. In US units, that is 32.2 feet per second squared. In SI, it's 9.81. I tend to use 9.81. I think there are some professors who use 9.8. I just go with 9.81 because if you carry that out, Round to 2 decimal places, that's what you get. So many problems are going to reference an object's mass, not its weight. So make sure you're dealing in forces instead of masses. Everybody good? All right, let me pull the notebook out. Let's go ahead and do our problem, okay? Okay, so I'm going to give everybody a sec to start copying this down if you need, but I'm going to talk a little bit about it, and then we're going to get into the wonderful world of statics today. So I have an object that weighs 400 pounds that is being supported by 2 cables that are at different orientations. And I want to know what the tension in those 2 cables is needed to be in order to keep the system in static equilibrium. Okay? Now, I want to make sure that we understand the engineering context. Why would I care about that? Like, why would I care about determining what the tension in these cables are? Who cares if one's carrying 300 pounds and one's carrying 200 pounds? Like, why do I care? Safety. Yep. Now, what's another reason? That everything you're saying, 100% right. What if? Well, let's continue that thought through. Money, right? That is another. So I tend to express engineering as walking the tightrope between safety and economy, right? What we're doing here is calculating the forces that these cables must withstand, and we need to understand that for safety. Because I can tell you right now, if I am standing right here, or my cat is standing right here, please, I'm an engineer. That's the best art you're going to get. But if this is my cat, I'm going to want to ensure that these cables are strong enough to safely support these loads. But, I mean, to hell with the engineering, why don't I just use cables that are this thick? It'll be fine. It won't be a problem. It'll cost too much money, right? So what we have to do is select cables that safely resist those loads, but are also economically viable, right? There's an old joke about this, that anybody can design a bridge. It takes an engineer to barely design a bridge. That's a joke, but there's a layer of truth in that statement, and then that's kind of the stuff we're talking about here. Okay, everybody good? Okay, so the first thing that we are going to do in this task is we're going to compute so the goal is to determine the tension in these 2 cables, but in order to do that, we need to assess the physics of the problem a little bit, and in order to do that, we're going to draw what's called a free body diagram. We're going to be drawing free body diagrams a lot in this class. But the long story short of a free body diagram is it is an illustration of the body in question and all of the relevant forces that are applied to that body. Now, for this unit of the class, remember, the name of this unit is the statics of particles, right? So what that means is, right now, all we're interested in is systems where all of the forces all meet at a common point. So what point am I talking about in this problem? I'm talking about point C, right? Now, how many forces are applied at point C right now? 3, right? The 2 from these cables and the weight. All right, so let's keep that in mind, okay? Now, before I draw my free body diagram, I just want to make sure everybody's paying attention on a couple things. What is the measure of that angle? 30 degrees, right? And what is the measure of that angle? 50 degrees. Okay, so if everybody is okay with that, let's get into some static slam. So the first thing that we're going to do is we're going to draw a free body diagram. And often in this class, I will just do this. FBD, okay? Now what we're doing is we're drawing that free body diagram for point C. That's what we're drawing. Okay. Now, here's what we've got. So here's point C. we have three vectors that are going through point C, okay? Now we have this vector right here, and what I'm going to do is I'm going to call this vector TBC, okay? So I'll write that a little bigger up here so that you see what I'm talking about. TBC. So that is the tension in this cable, and we were talking about BC because it's going from along that line, BC. We also have another vector like this, which is TAC. Now let's not forget our angles. We have one more vector, which I'm calling W. W for the weight. Okay? So far, so good? Sound good? Okay. Now, so here are our vectors. Now, what I'm going to do is I'm going to take a second and I want to write descriptions of these vectors. So, in IJ notation. Okay? Now, I want to explain what I'm going to do here in a second, and I'm going to do that over here with a little thought bubble. So, let's say that I had some vector F, okay? So, let's put that over here. Here's F, and it is at some angle theta. Now, how do I write that? So there's some pile of junk times I plus some pile of junk times J. What goes inside the brackets right here? What goes inside there? Say it again? Okay, but how would I write that mathematically? That's right. But okay, now I'm just talking about a single vector. Just ignore this. If I wanted to describe a single vector in IJ notation, how would I do that?
Force of cosine theta plus force of sine theta.
Say that again. Say it louder.
Force of cosine theta plus force of sine theta.
That's right. That's 100% right. Okay. So what I do is I put the cosine of theta here and the sine of theta here, but then I also have to include the magnitude. I have to put the magnitude of that vector here. Okay, so mathematically, the x component is f times the cosine, the y component is f times the sine. Does that make sense? But I got to include both the magnitude and those trigonometric functions. Okay? So with that, let's describe these vectors. Okay? So I want to start with vector, bless you, AC. Now vector AC is going to be some pile of junk times I plus some pile of junk times J. Now, this is vector AC, so we're talking about this one right here, and the angle is 50 degrees, right? So, would it be this? Would it be TAC cosine 50 degrees, TAC sine 50 degrees? Or did I forget something? What did I mess up in just now?
Cosine needs to be negative.
Exactly right. This one's negative. The cosine's negative because we're in the negative x direction, positive y. Does everybody see how I did that? And notice how inside I have the magnitude. So this is the magnitude cosine, magnitude sine. So what I'm getting at right now is I've got one vector described in IJ notation. Theoretically, I can describe all of them in the same notation. And if you notice, there is a reason that I am lining them up like this that you will see momentarily. There is a reason I'm writing it like this. So somebody help me out with TBC. How am I going to describe that? What's the x component going to be? $30 degrees. Is that positive or negative? Exactly right. What about this one? And is that positive or negative? Both of them are positive because we're in quadrant 1. So there we go. Okay. Now what about the weight? What goes in here? 0. This is a vertical vector. So this is 0. What about right here? Say again? Negative W. And what is the magnitude of W for this problem? Say it again? 400 pounds. So this needs to be negative 400 pounds. I would argue, I know this sounds silly, but that's actually one of the hardest parts of this problem is just to make sure that the vectors are described correctly, and specifically that you've included the magnitudes. It's very easy to forget that, and it kind of makes the algebra a little wonky a little later. So, bless you. So far, so good? Okay. Now, if I were to add up these 3 vectors, what must the sum of these vectors be? 0. For static equilibrium, that 400-pound weight can't move, all right? Because if that 400-pound weight were to move, my cat would be in trouble. I don't want anything to happen to my cat. My wife would not like that very much, okay? So what that means is the sum of these vectors must be equal to 0. But because I've written them in IJ notation, what that means is that the sum of the x components must be 0. The sum of the y components must be 0. Hence, why I've kind of written them in this vertical fashion like this. So now we are going to employ the equations of static equilibrium. So in 2 dimensions, we have 2 equations of equilibrium. The first is the sum of forces in the x direction is 0. Sometimes you will see, folks, when they're summing forces in the x direction, you might see this in the textbook where they do that, where basically what they're saying is that any force that's positive would be a force to the right. You don't have to write that in this instance because we've already accounted for that in our sign convention. Excuse me. But if you see that, I wanted you to know what that meant. Okay, so what this means is that I'm going to basically take all of these components and add them up. So, negative TAC cosine 50 degrees plus TBC cosine 30 degrees plus 0 equals 0. Okay? Okay. And so what we'll do is we'll call this equation 1. However, I'm going to rewrite it just a little bit differently. this might seem very superfluous. It might seem like a wasted step. You'll understand why I'm doing it here in a second. I'm going to take the variable out and put all the signs in parentheses. Okay, we're going to call this equation 1. Okay, which again, by the way, if there's any of my handwriting that you cannot read, let me know. Okay. Okay. Now, when we sum forces in the y direction, so what we'll do is we'll sum forces in the y direction. And similarly in your textbook, you might see something like that. So that means that every force that's acting upwards is positive. So if you see that in your textbook, that's what that means. But again, the signs already account for that. So we have, what we're doing is we're, again, adding up all of these components here. Again, why I think there's some value into taking the time and actually neatly formatting your calculations is it makes it easier to do the math. So TAC sine 50 degrees plus TBC sine 30 degrees minus 400 pounds is 0. Now, I'm going to rewrite this equation as well, and there's a specific way I'm going to go about this. So what I'm going to do, see how I have TAC times a constant plus TBC times a constant equals something? I'm going to write the second equation in that same format. So TAC times a constant plus TBC times a constant. And then what I'm going to do is I want that to equal something, so I'm going to move the 400 pounds over to the other side of the equation, and that makes that a positive 400 pounds. And this is equation 2, okay? All right. I'm going to stop for a second. I want to make sure everybody understands what I've done so far. Everybody okay with this? So let's go through the, yes, sir.
What happened to the negative on the angle?
The negative on what?
On the 50-degree angle. Because wasn't it measured from
Right here. Is this one?
yeah, and it's sine. Wouldn't it be in sine too?
So, let me see. So the vector was going up like this. So I think that this part was negative, but that part was positive. Because the y component's going upwards. If the vector was going down like this, it'd be negative, negative. Did that answer that? Everybody else okay with that? Okay. Don't hesitate if you got a question. Again, somebody's putting cash money on the table for you to be here. I want you to get your money's worth. So, everybody good? Okay. So, I've got 2 equations and 2 unknowns. Now it's time for me to solve them. Okay? So, solving the system. So, let me rewrite the expression. And then what I'm going to do is I'm going to write this in matrix notation. Now I want to stop for a second. To be clear, I could theoretically use substitution or elimination. But I think based on the trig functions that we've got here, we don't have like 1x plus 3y equals 7. The numbers are kind of messy. I mean, the sine of 50 degrees is going to be like 0.46, whatever. So using substitution or elimination, I think those elementary functions will work theoretically, but by hand it'll be kind of messy. Hence why I think this is a perfect problem to just leave to the calculator to figure out for us. So we're going to rewrite this in matrix notation. Now how that works is we have a table of values, we have our unknowns, and then our constants over here. That's what this is going to look like, okay? So let me help you fill this out. So over here is our unknowns. So this is TAB, or TAC, TBC. Over on the right is the 0 and the 400. And then on the left, I just put in my coefficients, okay? And I like writing my coefficients with the signs inside the parentheses because it helps me keep track of the signs a little better. So this one's negative, everything else is positive. So sometimes you'll see folks write it like this. They'll put a little thing like that so you can kind of differentiate. And so writing it in this fashion makes it really easy to plug and chug into one of our lovely calculator devices. Again, you could do this by hand if you want. I just think it ends up being a little messier than just letting the calculator do it. I might actually show you real quick how to do this in Excel because you're engineers. You should use Excel whenever you can. So using the Casio, so you go to mode, five, and then 1. And then the table that you end up putting in is negative cosine, 50 degrees, sine, 50 degrees, cosine, 30 degrees, sine, 30 degrees, and then 0 and 400. So that's the table that you end up putting in. And what the calculator should spit out to you is an answer for X and an answer for Y. I'm curious if somebody can do this and tell me what you get. I'm going to show everybody how to do this on Excel here in a quick second. By the way, remember this is recorded, so if some of the Excel stuff goes a little fast, you can always go back to the recording. So. Now, one thing I will tell you is that for a problem like this, there's a surefire way of seeing whether or not you did it correctly, or at least you should have something that resembles correctness if both of these answers are positive. These are tensions in cables, so they should be positive answers. They have an answer?
351.7540x.
So 351.75. And then over here.
61.08.
All right, does everybody have a second on that? Okay, so the calculator spit out X and Y. It doesn't know which is which, but we wrote this in a very specific order. Notice how we wrote TAC first, TBC second, TAC first, TBC second. That's TAC, that's TBC. So therefore, we know that cable AC must carry 351.75 pounds. TBC must carry 261.08 pounds. And that's it. Now we can select cables that hold up, that can hold up that much load. And Dr. Michelson's cat doesn't have anything to worry about. Rugen will be very happy. All right. Any question on this? All right, I do want to show you all how to do this calculation using Excel because I'm an engineer and I can't help it. So I want to show you that real quick. So just so you all are aware, so what we're going to do, we're going to fill in those 6 numbers that we just filled in here. So this was 0, this was 400. Now the way that we do this in Excel is we say, okay, first off, we have a negative cosine of 50, right? Wrong, because Excel deals in radians. So what we need to do is the cosine of the radians of 50. Then we have that. So we have that. That's not what I wanted. That. Then we have that. So is everybody okay with that? Okay. So let me show you how you do this in Excel. So the first thing that you do is maybe over here off to the side. Okay. What we're going to do is we're going to highlight all this and we're going to say equals M inverse. And what we do is we highlight this array. And what that does is that computes the inverse of that array. Then maybe over here, we say M mult of that and that. So what we do is we just take the inverse of these numbers, multiply by that, and by golly gosh gee, there's your answer. So that's not too bad, right? That's simple. We could do this in MATLAB if you would like. Does this computer have MATLAB on it? Hold on, let's see. Hey, look at that. Everybody loves MATLAB, right? I'm disappointed. I'm very disappointed. Would you like me to squeeze in some MATLAB, or would you like me to give you 2 minutes of your life back? I'm not going to show you the MATLAB. I'm leaning into it. All right, everybody. That's all I've got, everybody. I will, hey, in all seriousness, I will post a thing to Teams to show you how to do 2x2 solution for other calculators. One thing I will say, real quick, help me out. I'm going to make a post on that. If your calculator's missing, let me know and I'll see if I can find it. I'm going to pull the QR code back up. That's all I got. I will see you all on Friday.